Okay, so thank you to Douglas for the very kind invitation to present and also the introduction today. During my talk today, I'm going to try and tell you a little bit about battery materials and just generally where battery research sits within the current sort of energy landscape. So we all know that there are currently two major challenges within energy-related research. These are the declining world reserves of fossil fuels and the rapidly rising CO2 levels. Now, we also know that there are many possible solutions to these challenges, including decreasing our usage of fossil fuels, reducing our CO2 emissions by increasing our own efficiency, adopting carbon capture methods, or increasing our use of renewable energy sources such as solar, tidal, and wind. Now, whilst renewables are excellent in their ability to provide energy, they're notoriously intermittent in their ability to provide that energy on demand. So what we really need is a method for storing the energy that they provide that we can then use at a later date. And batteries could potentially be the solution to this problem. So it could be that we could use, well, at the moment, we know that there are numerous commercial batteries available for use, but can one of these batteries be used as a possible energy storage solution? But when we're thinking about this, given the world we currently live in, we need to start to think about environmental factors. So the materials that we're using in these batteries, are they leaving an impact on the environment? Should we really be using them? And there's all these sorts of questions around this type of research. So I guess the question we really have is, can batteries be used for large scale energy storage, which is what we're interested in? So at the moment, there are two main classifications of batteries, both of which you'll be familiar with, and you probably use them in every part of your daily lives. So the first is primary, or they're typically referred to as single-use batteries, and the others are secondary or rechargeable batteries. So primary batteries are things like your alkaline batteries or the 3-volt lithium batteries, which are often referred to as button cells. Now, these types of batteries are typically used in most handheld type devices that are in your house. So for example, your TV remote control, torches, various things like that. And as the name suggests, these batteries are disposed of once you've used all the energy from the battery, and then you replace it with another battery. And this is in contrast to secondary or rechargeable batteries, which again, you'll be quite familiar with. So your cars, for example, use lead acid batteries, and you know that you use your car over and over again and you don't need to replace the battery. And that's because that battery is rechargeable. And it's the same for your portable electronic devices, such as your laptops, mobile phones, tablets, etc. In this particular case, they're using lithium-ion batteries. And these are the main applications for these types of batteries, these secondary or rechargeable batteries. And it's lithium-ion batteries that I'm going to concentrate my discussion on today. So rechargeable lithium-ion batteries have undoubtedly revolutionized global communication and the technology industry within recent years. Now, all batteries are the same in that they're all composed of the same three main components. We have a positive electrode, a negative electrode, and these are separated by a lithium conducting electrolyte. Now, the actual materials that make up these batteries depend on the type of chemistry that's taking place, if you like. And in current commercial lithium-ion batteries, the positive electrode is composed of lithium cobalt oxide, and the negative electrode is composed of graphite, which is carbon, essentially. So during operation, the lithium ions from the lithium cobalt oxide, which are shown in light blue here on the right, will migrate through the lithium conducting electrolyte, and they'll insert or intercalate themselves between the layers of the graphite in the negative electrode. And then upon discharge, so a reversal of the current, those lithium ions will return back to the lithium cobalt oxide, making this a completely rechargeable and reversible process that's taking place. And this works really, really well. As you know, it works in all your handheld devices, all your portable electronics. Now, over the years, many people have tried to change various different components of the lithium-ion battery. So we've had developments on the negative electrode, so changing it from being carbon-based to something else. Similarly, we've done the same for the positive electrode, changing that lithium cobalt oxide, and we've done the same for the lithium conducting electrolyte. But in all cases, these new materials that have been tried and tested haven't given as good a performance as those initial materials that were commercialized by Sony in 1991. So actually the components we use now are still those that we first used in the very first commercialized lithium-ion batteries. And the simple answer is that it just works well, and actually it gives us the best performance that we can have. And there are many advantages associated with lithium-ion batteries. So these are compact, they're lightweight because they're using lithium as the mobile source, or the mobile species rather. They give high energy densities, they can charge very quickly, and they ultimately have quite a long lifetime. But like with everything, there are some disadvantages to these materials as well. Some of the main disadvantages of lithium-ion batteries is that they're quite costly to produce. Ultimately, they do have some aging effects. Eventually, that battery will need replaced. There are some quite serious safety concerns, which I'll come on to in a second. And there are also some serious questions regarding some of the materials or the raw materials that are used to make some of the components of the battery. So for example, you have lithium within the lithium cobalt oxide. We need to obtain lithium from somewhere, and that brings into doubt some of the questions regarding lithium reserves that are available globally. Similarly, there's cobalt in the lithium cobalt oxide, and there's some geopolitical challenges associated with cobalt mining. Now, one of the greatest challenges associated with current commercial lithium-ion batteries is the use of liquid electrolytes, which are known to pose some very serious fire and safety risks. And that's ultimately because the liquid that's used as the electrolyte is a highly flammable liquid. So ideally, what we would like to do is change or replace that liquid electrolyte for a solid state equivalent. And in doing so, we would produce an all solid state lithium-ion battery. And ultimately, that would help to improve the safety of these batteries. But like most things in research, this isn't really that easy to do, because it's not just a case of replacing directly that liquid electrolyte with a solid state equivalent. We need to make sure that the material that we replace it with has a high enough ionic conductivity. It needs to be equivalent or better than the current commercial lithium-ion batteries that we have. Similarly, if we just place a new material inside the center of a battery, how do we know that it's compatible with all of the other components of the battery? So really, this is what makes this quite a challenging problem, in that there are many things to think about, not just the conductivity of that central electrolyte species. Now, in recent years, lots and lots of different materials have been investigated as possible solid electrolytes. I'm not going to go through any of the details of these ones here. It's just to give you an idea that actually what we're trying to do in terms of materials research is we're trying to look for structures where those lithium ions can move as easily and freely as possible through these materials. So looking for channels and easy pathways for those lithium ions to move as effectively and as efficiently as they possibly can. Now, of the structures that are shown here, some of the work that I've been doing in my research group concerns these garnet materials shown on the bottom left, and also these lithium-rich antiperovskites shown here on the bottom figure. Now, these lithium-rich antiperovskites have shown quite considerable promise as solid electrolyte materials, and this is work that I've been doing in collaboration with a computational chemist at Newcastle University, Dr. James Dawson. And this is a project that we're continuing to work on through structural manipulation and trying to understand how the structure really influences those pathways for those lithium ions to move within these materials. So there are some real significant challenges associated with developing all solid state batteries. So as I said, it's not just about finding a material that has the highest ionic conductivity. You have to think about how that material is going to interact with all other species in the system or in the cell. But in addition to this, you need to think about those raw materials that are going to be needed to prepare the materials that you need inside your battery, and in particular in your solid electrolyte. Can these materials be recycled, for example? Can we reuse them? Can we obtain them from the Earth's crust in an environmentally friendly way without any issues occurring? So some of the requirements for all solid state batteries, or in particular for solid electrolytes, are the materials must be safe. That's a real top of the list sort of thing as to what we need to tick off. They also need to have a high ionic conductivity. Remember, these need to be equivalent or better than the current market leaders, i.e. those batteries that were commercialized by Sony in 1991. They also need to have large electrochemical windows. They need to be relatively cheap to produce so that we can scale these up eventually. Again, they need to think about the environment, and they need to be compatible with all of the other materials in the system, as well as having stability as well. So batteries really are a promising future energy storage solution. And ideally, if we were to think about this cycle that's shown on the screen here, we would like to be able to use renewable energy to generate, or renewables to generate our energy in the most green way that we can. We would then like to use batteries to store the energy that's produced before then disseminating that energy onto things like electric vehicles or smart houses and any other green applications, green energy applications that we can. Now, thinking about this, there's been huge step changes in performance with regards to renewable energy. So the generation of the energy has come on leaps and bounds in recent years. And similarly, electric vehicles and smart devices and smart houses, they're all coming on leaps and bounds as well. And if we were to think about it, the bottleneck in the sort of system really is the energy storage via batteries. Because if you remember, the batteries we're currently using are still using the same chemistry and the same technology that was initially commercialized in 1991. So we've not made that current step change in performance that's needed in order to bring batteries into the next stage that's required to really get this energy storage to actually happen and to occur the way we want it to. So we still face some significant challenges in the world of battery research. And as I've said before, it's, performance. We need to have materials that perform well, that better than current systems that we're looking at. We need to have materials that are safe and reliable, that can be used without any worries, including compatibility issues. So they need to be safe and work well with the other components of the cell in order to get that performance. We also need to think about our environmental impact. Are any of those components able to be recycled after use? Can we bring it to, so it has a nicer life cycle, I guess, of the materials? And we also need to think about, the use of finite resources. Can we avoid that in any way? And then the biggest question we have is, can actually we use the lithium-ion technology that we know works well for portable electronics? Can we use that for large scale applications, or is it just not going to meet the need for the large scale applications? So for example, for grid storage. And actually that's when we need to start thinking about beyond lithium ion. So can we move on to things like sodium or magnesium ion technology? And that's a huge area of interest that's still being explored. It's not as simple as just changing from lithium to sodium or magnesium. The chemistry is not the same, the materials don't work in the same way. So there's a lot of investment and time and energy that needs to go into understanding how these types of materials perform. And ultimately, everything we produce or use needs to be safe, sustainable, and environmentally benign. We can't be damaging the environment with the materials that we're trying to produce. So this was sort of an overview of where batteries have started, where we are with them now. Obviously, it's such a large field, I can't cover everything, but it's just highlighting the sort of areas that we're thinking about, where we're moving forward to, and really thinking about how the chemistry hasn't changed quite so much as we would have liked at the current time. So I'll finish there by thanking you for your attention, and I'm happy to take any questions at the end of the session.
Lovely. Thank you very much, Karen, for a fascinating sort of overview and insight into some of the challenge associated with batteries. We take batteries for granted so often and don't really give them a second thought sometimes. So it's really nice to hear, some of the challenges at the forefront of this technology in terms of meeting the growing need for energy storage. So thank you very much.